So good evening, participants. Thank you for joining your today's webinar. And the topic for today's webinar is Analytical Modeling of Modular Multilevel Converters and Circulating Current Control. The webinar will be handled by Dr.Abhijit, Kshirsagar, faculty from IIT Dharwad. And on behalf of IAS, IES, PLS Joint Chapter Kerala, I welcome all the participants to this webinar, and I request Dr. Abhijit for the presentation. Abhijit, please.
Hello.
Yes.
Can you all hear me?
Yes.
All right, perfect. So first of all, thank you to the IAI Joint Chapter for giving me this opportunity. I was a little hesitant at first, but with their encouragement, I thought it's a good way to make use of this time when a lot of conventional things we cannot do in our education efforts, right? So what I want to talk about is something that I've been working on during my postdoctoral work. Just a little bit about myself. I'm currently a faculty member in the electrical engineering department here at IIT Dharwad. For those of you who don't know, Dharwad is one of the older cities in Karnataka. It's been like the center of education since ancient times. It's situated in North Karnataka, about halfway between Bangalore and Mumbai. And so this is a new IIT, this is a third generation IIT. And we have a very strong electrical engineering team that is in force here. So the work that I'm going to talk about is something that I did just before I joined IIT Dharwad. I was in Professor Ned Mohan's lab at the University of Minnesota, where we were doing a lot of work on modular converters, modular multi-level converters. And so the content that I'm going to talk about is not exactly research work, but it's sort of the foundation for a lot of work that we have done. And so the objective of today's seminar is to sort of familiarize all our listeners to what are MMCs, what is the circuit topology like, some definitions, and then we'll get into steady state circuit modeling and analysis, because the whole point of this seminar is to do mathematical modeling. And so what I want to focus on is first look at the circuit a little bit, and then I will get into the mathematical analysis and the converter and modulation schemes that are used. So I'm not going to go into a lot of detail because there's a lot of work that has already been done on MMCs. If you just open IEEE explore and search for MMCs, you will get a variety of papers, whether it is modeling, whether it is circuit design, whether it is controls, and so on. So there's lots of things that have already been done. One thing that I want to focus on sort of different is to convey some intuitive understandings that I think that may be useful for some of the new, so for people who are new to this field. And I don't want to get into just bog down in the equation, the math. The math, of course, I will cover, but I think conveying this intuitive sort of understanding will be helpful in reading papers and understanding newer techniques, and as you read other people's research as well. Then I will touch on capacitor balancing, because that's again one very important part. And then finally I'll go to analysis of circulating currents, because that's again one of the key things in MMCs. One final sort of note here is that some of these things are in MATLAB model, and if we get time, what we're going to do is I'll show you some of those. And so somebody says not audible. Is Eldo online? Eldo is there?
Dr. Abhijit, you are audible, but they
Okay.
may be asking what the voice level, maybe.
Do you think I need to be louder?
They may be requesting for that, actually. The voice level is little bit low, but
Okay.
it's audible.
Okay, just hold 1 second. I will try to move myself closer to the mic. 1 second.
Okay, fine.
Okay, does this help?
So they're feeling some echo in your voice. I think
There's still an echo?
Yeah, there is
Yeah, small echo is
small
there. Yeah.
Small echo is there. Well, I'm on headphones, so I don't know. I'm not sure what else we can do here.
So can you just try without headphones? Will that work?
Let's try. It may actually make the echo worse. Can you hear me now?
Yes. Can you repeat? Just repeat.
Yeah.
To
Can you
check.
hear me now? Is this better?
Yes, I think. What about Eldo and all? How do you feel? Hello, Alan.
Yes, sir, audible.
It's audible, sir.
Yeah.
Better than.
So which is better actually, with the headphone or without headphone? Okay, Abhijit, I think you can proceed without headphone. We will see. Okay.
Okay. If at all there is too much disturbance, then we'll see. Let me just try and move myself a little bit. Okay. Okay. So just continuing. What I want to talk about is then finish up with circulating currents, and then I'll talk a little bit about how to make the model in MATLAB, and I'll show you some simulation results also. Okay. So coming up next. Let me see if I can scribble on this. Okay, so now, so a quick introduction to MMCs. I think everyone's heard MMCs like a buzzword. Essentially, MMC stands for Modular Multilevel Converter. It's an AC to DC converter, bidirectional, of course, so it can convert power from AC to DC and DC to AC. And it became popular specifically because of applications in high voltage and high power. So it was originally conceived for HVDC links, where you need to transfer transmission level voltage and power from one grid to another, or long distance power transmission. And there were a lot of benefits of using HVDC. And conventionally, before semiconductors were popular, devices like mercury arc valves were used, and so those, of course, were not as preferable due to maintenance issues. So when semiconductors came along, this topology that is called MMC now, that really enabled HVDC to become very popular and very cost effective and efficient for power transmission. So that's where it got its start. It's essentially, as shown here, it's basically a three-phase AC to DC converter. You have three-phase AC coming in one side, and then you have a DC link in the middle. This DC link could be a short DC link, it could be a long wire. And in many cases, okay, there's one more. Yes, I'm presenting screen. What happened? Oh, for some reason my screen share has stopped. Sorry, 1 second. I think okay, optimize for full screen. Can you see my screen now?
Yeah.
Okay. Thank you. Sorry about that. I think Eldo or someone, if you have any issues, just feel free to interrupt me over voice.
Yeah, sure.
Because when everything else is minimized, I can't see anything except my own screen.
Okay.
So what I was talking about is this converter scheme where you have three-phase AC coming in here, and then that's converted to a DC link, and then DC link is converted back into an AC. And this is where HVDC MMCs really found a lot of favor. So now, of course, we've gone beyond HVDC applications. Now they're applied to industrial drives. They're now finding favor in renewables, especially in wind energy, where converters that have a small footprint are desirable. And so a lot of benefits are there in all these extra newer applications. So that's why students and power just came back just maybe a few minutes before this was supposed to start. So we are lucky. Let's try to get back on track. So what I was talking about is that MMCs have found favor beyond their original HVDC application. Now, what exactly is MMC? So MMC is modular, which means consists of a large number of identical modules. So these modules are initially called valves, because of the terminology that comes from the mercury valves time. They're also called cells. Sometimes they're called submodules, but essentially you have to remember that the topology consists of a large number of identical units. Now, they are identical because of which, there are a lot of operational and maintenance benefits. In case one module fails, it's possible to quickly replace it. It's possible to have the topology with multiple additional modules already in place that allows fault tolerance. It's possible to keep some modules in stock as spares. So operational wise, there's a lot of benefits. So the other thing is it's a multi-level converter. So just a quick review for those of you who don't know multi-level converters. A conventional two-level inverter, right? A conventional two-level inverter produces two voltage levels, let's say some 0 and 1. Right? The problem is that it has poor harmonic performance, as in we want to generate a sine wave, as you can see in blue here, but the inverter can only produce square waves or rectangular waves, that as shown in green. So the problem is this harmonic performance is poor, dV by dt is high, and dV by dt means voltage transient. So the voltage goes from 0 or off to full value very quickly. And that is very, very detrimental for a lot of reasons. And I won't go into those right now. But imagine doing that when your DC link is, hundreds of kilovolts, which is common with, let's say, medium voltage drives or HVDC applications. So those cases, dV by dt is completely unacceptable. So the better thing is to do some pulse width modulation, to do harmonic filtering, which you can do with two-level inverters. But the dV by dt problem is still there. So what you can do is that these inverters can be designed to produce multiple levels. So we can have n levels, and you can see this waveform has this staircase type shape. So essentially what we have done is we have reduced the step size. Instead of going from 0 to full, we are going in smaller steps, let's say n steps. And because of this, first of all, harmonic performance is improved. We don't need filters. dV by dt is much lower, and the number of steps that this topology produces, or an MMC produces, is roughly proportional to the number of modules that we have. So more modules, more steps, you don't need to. So dV by dt is lower, harmonic performance is better, and so on. Essentially what we are doing is we're producing a staircase shaped waveform, which is not ideal. The ideal is of course a sine wave, but it's very close to ideal. It's close enough to this ideal sine wave that we want to produce. So if n is large enough, so we don't know what that large enough is yet, but if it is large enough, this stepped waveform or the staircase waveform is enough for these high voltage and high power applications. So the key benefits, of course, I've already covered. They're low THD, lower filtering requirement. It is scalable, and there's no real limit on the DC bus voltage because the modules themselves are low voltage rated, relatively low voltage, I should say. It's possible to cascade really any number of modules. There's no physical limit, or there's no essential limit on how many modules you can stack. And there's redundancy from the use of identical modules, which gives you operational benefits. And the other thing, of course, is that we are using low voltage devices to realize high voltage output, which is a big bonus, because you don't have devices that can tolerate transmission level voltages anyway. So the challenge is that because of this modularity, there's a large number of modules, so large number of floating capacitors. The problem is that all these capacitors must be sensed and controlled, and we'll see all these challenges when we look at the topology. The second problem is that the capacitors see fundamental frequency currents, because of which they need to be sized to handle that ripple. And again, we'll see that in the forthcoming slides. And there's also a problem of circulating current, which needs to be controlled, which is the last portion of my presentation today. The last bullet is something that I know is a problem, but I can't talk really much about what the solutions are. And that is the physical and system design. For instance, I know someone who works on physical layout of complex inverter topologies, and managing things like creepage distances, insulation, safe distances between components that are at different values, right? So all those things are already challenging, but with an MMC, they have additional challenges. Plus, you need to have cabling or controls that go all over the place, right? From all modules, you need to sense voltages, you need to control, provide gate signals. So it's a fairly challenging problem. Now, let's look at some of the modeling challenges. So a topology that is this complex, first of all, has a large number of devices. And to simulate it in switched mode, meaning switched models, on like a regular desktop, it takes long simulation time, needs a lot of resource usage, a lot of memory, and so on. It's very hard to capture things like device variation, mismatches between modules, and things like that in normal simulation models. When you want to test controllers, when you want to develop control schemes, it becomes necessary to have some sort of a simplified model or some sort of an abstracted averaged model in order to be able to do that. And we'll see some of those models in the coming slides. And systems like this, meaning an MMC, is often not simulated by itself, right? So it's part of a larger system involving, let's say, transmission lines or some other components or some sources, loads, and so on. And so you want this, you want a good model that simulates quickly and accurately to be able to do system level simulations, and especially in cases of scenario management. For instance, there would be something where you're exploring possibility of faults, possibility of multiple faults, possibility of sequences of faults, and so on. So in those cases, it's good to know modeling and simulation very well for these systems. One of the other things that a lot of people are doing is to simulate MMCs and similar systems in real-time simulators like an OpenRT or Typhoon-based systems. So what these systems do is they use proprietary tricks because they have solvers and they have their own proprietary software that they have developed to get fast and accurate simulations. But in many cases, these are expensive hardware, software, and it's not always feasible to do it on such a system in many cases. Okay, so now let's start looking into the MMC topology. Any questions so far? I am not able to see any in the chat, but if anyone has questions, feel free to just pop something in the chat window. Okay, so let's start now diving into the topology. So the topology, as I said, consists of all of these submodules that are cascaded in series, right? So submodule 1, 2, 3, 4, all the way to n, and each of these submodules looks like this. In this case, I have shown just one submodule or a cell, and the most common type of submodule is what is called a half bridge. Now, anyone who is familiar with power electronics probably knows what a half bridge is. It's essentially just a DC source. In this case, this DC voltage comes from a capacitor. There are no DC sources. In this case, the voltage of this capacitor is some nominal value. We call it V cell. And there are two switches that generate this output that is taken across here. So these are the two terminals of our cell, and they're all cascaded in this chain that you see. Okay. Can you please elaborate? So there's a question, can you please elaborate on the point capacitors only see fundamental currents? So let me clarify that. Capacitors don't see only fundamental currents, they see other components, and we'll talk about that. I have a whole slide on modeling and the equations for that. So we'll get to that in some time. Okay. So converter, in one converter, all the submodules are identical for the simple case. There are, of course, topologies which have been produced where submodules are not identical. Some of those are called asymmetric MMCs and all. So we won't get into that for now. Also, the thing to note is that this submodule can produce only two output voltage levels measured across these 2 points here. The output voltage can either be V cell when the module is on, or it can be 0 when the module is off. Right. So those are the only 2 output voltage states that are possible. The submodule voltage is measured with this polarity. That's just by definition. And the capacitor voltage is nominally assumed to be V cell. And for the remaining discussion, we'll say that if your converter is designed properly, working properly, the capacitor voltage stays nearly V cell plus or minus some ripple. We don't expect it to fall significantly below or above this value. Okay. So what happens when, now of course there's a capacitor, so it can charge or discharge. So what's going to happen is that when a current flows through this branch here, it flows through all of the submodules, and the same current flows through SM1, the same current flows through SM2, and so on and so forth. But depending on the state of the module, depending on whether the module is on or off, there are 3 possibilities. The first is the module is on, and current is flowing in this direction. In that case, this capacitor is going to discharge. That is case number 1. Case number 2 is the module is on, but current is in the opposite direction. That causes this capacitor to charge up. So essentially you have current flowing like this, capacitor voltage is measured like this, and so capacitor voltage will increase. So you have two cases when the module is on. Based on the line current, capacitor will either discharge or charge. Now, just a quick point to note here is that when the module is on, right, it is important to note that the controller or whoever is controlling this topology has no choice of whether this capacitor will charge or discharge, right? So based on the current direction, based on this current direction, it will either charge or discharge, and we cannot choose between these two. The only thing we can choose is whether it is affected or the cap stays unaffected, and to do that, this module is simply bypassed. So no current flows through the capacitor, and capacitor voltage is unaffected. So now just some definitions. One set of these submodules, along with a filter inductor called an arm inductor, this whole thing is called an arm. So what you can see is that this arm consists of n submodules, all connected in series, one inductor, and the voltage across all of these submodules is essentially just the sum of the voltages of all of these individual submodules. We call that upper arm voltage, VUA, right? So just to recap here, there are n submodules in series. The voltage VUA is just the sum of all these, and so it can range only between 0 when all modules are off, up to n times V cell, where again V cell is assumed to be the nominal voltage of each of the capacitors. So we cannot exceed that. So other thing you should note is that VUA, when measured in this direction, can only be positive, right? So because it's because each cell is a half bridge, it can produce only 0 or positive voltage. As a result, VUA can only range between 0 to n times that cell voltage, right? Also, because each module can be on or off, the arm voltage VUA can vary in discrete steps, n plus 1 discrete steps corresponding to 0, 1, 2, 3, and so on, up to n modules being on. So when all modules are off, the voltage is 0. When one module is on, the voltage is 1 times V cell. When two modules are on, it's 2 times V cell, and so on, right? So with n modules in this arm, we've got n plus 1 discrete values. So n plus 1 voltage levels that can be produced at VUA. Okay. So similarly, we have the lower arm, exactly the same thing, no change. And just in case anyone was wondering, this cell that was connected in this direction for the top one is connected exactly the same way here also. So this was plus, minus here, this is plus and minus here. So no change, no other change, right? So that's all about these two arms, and we have 6 of these arms for each phase of the 3-phase converter. So we have a total of 6 arms. Okay. The arm is also included in the yes, sorry, clarification. The arm should consist of all of this. So the arm consists of the arm inductor also, right? Next. So now every phase, there are 3 phases in this converter. Each phase is what is called a phase leg, and in each phase has 2 arms. So this is a very bad MMC joke, is that only in MMC you will get 2 arms that constitute a leg, but that's how it's called. That's some legacy terminology. So each phase or each phase leg ends up having 2 n submodules and these 2 arm inductors. One of the things that I have not marked explicitly here, but is sort of taken for granted, is the fact that these arm inductors are not pure L. Now, in any physical system, of course, the L has its own resistance, series resistance. So we are not going to talk about that right now, but just to keep in the back of your mind. The arm inductor has inductance as well as resistance, and that somehow affects our controller design later. But we won't go into that detail at this point. Okay, so next, then we want to look at the per phase circuit. So I didn't talk about how the DC bus was connected, just we had sort of brushed that under the carpet, but let's look at it now. If you had a DC source, then conventionally the way to do it is to represent the DC bus as two split DC sources with a ground point in the middle. And now this ground point in the middle is taken as the 0 point or reference point for all our voltages. That is what I mean by this global ground referenced split DC bus. Now, when we want to do all this modeling, one of the simple ways in which we can abstract out the converter behavior is to sum all of the instantaneous voltages of all these modules and represent that as a single voltage source. We call that VU. And similarly, for the lower arm, we bulk up all of the individual module voltages, and we call that the lower arm voltage is VL. Now, because this is a single phase representation, I just called it VU and VL for simplicity. But when we talk about three phase, it will be VUA and VLA and so on. Next thing to look at is that the current that is flowing out to the load is flowing out on this terminal, which is again called which we call the phase terminal. Okay. Now, one thing that I have sort of marked here but not explicitly mentioned is that this IA that is flowing out on this terminal, which is called the pole, is getting split half from the top arm and half from the bottom arm, but we'll come to that in a minute. Okay, so now let's look at it. Let's think about this topology in the fundamental frequency domain, right? So what we're going to do is we're going to neglect any drop across the arm inductors, and the assumption is valid because in the fundamental frequency domain, this is essentially a filter which is filtering out high frequency. So we don't really want this arm inductor to be having any significant voltage across it in the fundamental frequency domain. So in the fundamental domain, we make an assumption that let's say that this voltage needs to vary from minus VDC by 2 to plus VDC by 2 sinusoidally, which is very standard for any inverter with a DC link with VDC by 2, VDC by 2 split DC bus. So if we want to do that, we know what this voltage here should be. So I know this should be a sinusoid that looks like this, and the magnitude is say plus VDC by 2 positive peak to minus VDC by 2. Then what should VU and VL look like? That's the question that we need to answer. So let me get rid of this part. Okay. So first of all, now let's look at let's make some observations here. First of all, VU and VL must instantaneously equal VDC, right? Because if the sum of VU and VL okay, so if at any instant, if the sum of VU and VL is not equal to VDC, then just looking at this loop and putting Kirchhoff's voltage law, we'll see that a voltage will appear across these two inductors. And as you know, putting a DC voltage across these inductors is not a good idea. So let's say that, that's our first observation. We don't want a DC voltage across these arm inductors. So VU plus VL instantaneously, or at least in the fundamental average sense, must equal VDC. Then the other observation is that when this point is at the positive peak or the positive half cycle, what do we expect? This point is going to be at plus VDC by 2. That obviously means that the voltage across this source, or the voltage produced by VU, must be 0. Similarly, at the negative peak, VL must be 0, right? Also, the other corresponding thing is at the positive peak, VL must be producing the maximum voltage, and at the negative peak, VU must be producing the maximum voltage. So now just applying Kirchhoff's voltage loop law, voltage equation, gives us the fundamental average value of VU and VL, right? So we know what VA is. So VDC referenced, everything referenced to ground, 0 plus VDC by 2 minus VU going in this direction. Again, we assume that this drop is 0 equals VA, right? So that gives us a simple equation to find out VU. So I've just plotted this here in the in a quick MATLAB plot. So this is what, let's say, VA looks like this, right? And everything is scaled in terms of in VDC units. So you can say it's going from 0 to half VDC to minus half VDC and so on, right? So when this voltage looks like this, the voltage across VL, again, always measured like this, should be the sinusoid with a DC offset, right? Similarly, voltage across this source, VU, the top arm voltage, must look like this here, right? So what does this tell us? First of all, our assumptions are correct in that, both arm voltages are positive because H bridges cannot, half bridges cannot produce negative voltages. So upper and lower arms are both producing voltages that are only 0 or positive in magnitude. That's correct. And the other observation is that VU and VL are exactly 180 degrees apart, right? Which also we saw in our quick check that we did here. So they're 180 degrees apart. When fundamental is at its maximum, VL is maximum, VU is minimum, and vice versa, right? Okay, so that gives us fundamental steady state values for VU and VL, which means that we have all these modules at our command. We need to generate this VU and VL, and we have to modulate it somehow. So we'll figure out how to do that next. Then one other thing to look at is that we saw that the maximum value that this chain of modules or one arm can generate is simply n times B cell, right? So we know that we need to generate VDC as the maximum value. And if we have n cells, then each cell must have a nominal voltage equal to VDC by n straight away, right? So basically that tells us that the nominal voltage of each submodule capacitor equals the DC bus voltage divided by the number of modules in the arm. So essentially this point can swing all the way between 0, which is this node here, all the way to minus VDC by 2. And for that, VU should have a range of 0 to VDC, and therefore V cell must equal VDC by n, right? Okay. Next thing we should look at is that, now let's assume that these two are just two sources, right? Now what I can do is I can, in this arm or in this path here, I can bulk up this source and this source here into just another source, right? So it's one DC source plus one AC source. I can call this another voltage source, and I will put that here, right? I can do the same thing. Let me see if I can change the color here. I'm going to take this source and this split DC bus, and I'm going to put that as a second source here. Now they're indicated as AC, but remember that they're AC plus DC. We'll worry about that later. So essentially we have done that. So our circuit now becomes these two sources that are in parallel driving the load. So I haven't mentioned what is beyond this, but let's just say that there's some impedance on our load terminal. And what it's easy to see from this representation is that there are two sources that are driving this load point, and they're in parallel. And if these two arm inductors are nearly equal, or they're equal for all practical purposes, then it's easy to see that this current that is drawn by this load is going to split equally from each arm, right? So we have assumed that the arm inductors are equal, and as a result of that, IA must split half from upper arm and the remaining half from the lower arm. Now, if IA is flowing in this direction, you can appreciate that half that arm current is going to be flowing in this direction in the upper arm and in the opposite direction in the lower arm. So right now I'm doing a qualitative treatment of these things, because when you start writing your own models or you start writing your own equations, you have to keep track of whether you define your arm currents in the same direction. Do you define them going towards the load? Whatever convention, whatever you want to choose, you can choose. So I'm not going to stick to one of to either actually, but I'm just giving you a qualitative feel for all of these things. Okay. So now let's look at the common mode view of these things. So what happens if, let's say, VU were increased by a small amount and VL were decreased by a small amount? So let's go back to this circuit diagram where we want to look at the effects on the output, Z out, right? So essentially what happens is, due to superposition, if I were to increase this by a small amount delta and I were to decrease this by a small amount delta, there would be no effect here, right? Because this is like a voltage divider, and the effect here would be cancelled out. So that's what intuitively we mean to say, is that adding a small voltage offset to VU and subtracting that same offset from VL has no effect on VA, right? So effectively, it's like common mode that gets cancelled out at the load terminal. So we can do whatever we want as long as we add symmetric offsets and have no effect on VA. However, this net delta that appears across these two arm inductors, right? So what is going to happen is that net voltage will appear across this. So far, before this, we had said that we don't want any DC to appear, but supposing it does happen, and if those offsets are equal, then we can say two things: the offset has no effect at the output, and that offset appears equally across these two arm inductors. So as a result, this can cause a current to flow in this direction, like this, and that current will not go out, because as you have seen in this case, superposition tells you that there's no return path for that differential for that common mode. So that current is going to basically circulate like this, right? And that equivalent in this diagram is this current going from the DC source through the two arms and back. It does not go on to the output. So let's call this component the common mode component, or the DC component. So now let's see where this DC comes from and what is its value. What should it be there? Should it not be there? Let's take a quick look. Okay, so what we are going to do now is look at power balance. How are we doing on time? We started about 10 minutes, 10-15 minutes late, right, Eldo? So I think, yeah, we started about 10 minutes late. So I'll try to catch up and try to finish on time. Okay, so now let's look at that DC current that we said is going to flow. Now, if there's some DC component, the arm current in this top arm is going to be obviously this, plus whatever is this DC component, and whatever flows here, that DC component minus the phase component, which is IA by 2, is going to flow in the lower arm. So now let's just look at this average power seen by this source. Now, because VU consists only of capacitors, it's easy to say that it must not supply average power. If it supplies any average power, obviously the capacitors will discharge and the voltage will flat out. So we don't want that to happen. We don't want it to absorb any real power either, because then the capacitors will overcharge. So the average power delivered by VU must be 0. Now, average power delivered by VU is nothing but integral over one fundamental cycle, 0 to t, the instantaneous arm current as a function of time times the output of the output voltage of that arm. And we know that this arm consists of half of the phase component plus some IDC, and we don't know what this is yet. And it turns out that when this IDC, when P average is 0, this IDC has this form. So it has some value, and that value is now necessary to ensure that the arms do not deliver DC power. right? So this is the beauty of this topology, that these two arms are only capacitors. They are only doing sort of adding and subtracting voltages during the two half cycles. All the DC power comes from these two sources, the DC sources, and on average, VU and VL do not absorb any real power on a cycle average basis, right? So this should answer one of the questions that one of the attendees had, that was, do the capacitors carry fundamental current? And obviously you can see that each arm does carry fundamental current, and it cannot have zero power at any time period less than the fundamental cycle, right? So it charges in positive half cycle, discharges in the negative, and so on. Okay, so one other thing to look at, which I sort of skimmed through in this, is this value here. So you can see that IDC is actually proportional to the peak value of the output voltage, VA peak, and it's proportional to the ratio of this VA peak divided by half VDC. So this is, in some sense, the modulation index. So higher the modulation index, higher your IDC, which is expected, right? So you're delivering higher power, so your IDC is higher. So I haven't introduced the term modulation index for a very good reason here. We are not talking about modulation index. We are just talking about VA in terms of its peak value. So this is the expression, and if you look at pretty much any paper that introduces MMCs and their dynamics and modeling, these are some of the equations that you'll come across. But I'm just giving you a basic idea of where they come from and how you can get to them by first principles. Okay. So essentially what we have done is, by ensuring this P average equals 0 all the time, we have ensured that net energy in this arm, right? So half CV square in every module, half CV1 square, half CV2 square, and so on. The energy in that arm is maintained constant. If P is 0, then E must be constant, right? So what we have done is we have accounted for that total energy not changing. The other thing to look at is that the total arm energy is sort of a reflection of the average voltage of all the caps, right? It has nothing to do with the individual voltages. The individual voltages may still be away from their nominal values, but what we have done is looked at only the average or the total energy in some sense, right? The other thing is we want to control that arm energy in many cases. So sometimes, there's leakage in capacitors, they're maybe not ideal, or there are some transient dynamics for whatever reason. Let's say the arm energy is not where you want it to be. All you have to do is control this IDC, and we know that basically whatever is this IDC that is flowing, that charges or discharges the total arm energy. So if you increase IDC, your capacitors charge up, arm energy increases. If IDC decreases, then the capacitors discharge, arm energy decreases. So you want that IDC to be this value plus or minus whatever is your some error component, right? When you are trying to do arm energy control. So that's the IDC value that you want flowing through each arm of the converter at any time. Okay. So that's all about arm energy, and the way to do that is to have a control variable that essentially adds a DC offset to the upper arm voltage and lower arm voltage. Now, thing to note here is that VO and VL are sort of commanded voltages. It's the desired voltage that we want the arms to produce, and how they produce it, we'll see later. But for now, let's assume that if we want VU, we can get VU within, of course, the limits. Okay, so now we want to do DC current control. So we want to see what the system looks like. So we've already seen what the system looks like for the common mode sense. So it looks like this. And essentially what happens is that these two DC sources we can cancel out, because this is your DC value plus some offset. So you can bulk it up as some offset here, some offset here. And essentially what the system is, it's just a pure L or LR circuit, depending on whether you want to consider this as pure L or LR. And you can make a simplified model that looks like this. Just put your transfer function, simple first order system, design PI, and you can essentially figure out what your controller should look like. So essentially this transfer function has these two inductors, and it has a inbuilt capacitor that is integrating that charge, right? So that's your transfer function, design the PI, and what is the average voltage that we are trying to hit? That is like, let's say, the total voltage. So we'll see that in the MATLAB model when we get to that. So in this case, I'm doing a simulation where there are 4 modules up here and there are 4 modules here. So I want the total voltage to be VC nominal, the nominal voltage of the gap, times 8, right? So that's why that 8 is there. Next is modulation. So now we know what the arm voltage should be. We want to know how to get it, right? So here, this is a very nice simulation that is actually on Wikipedia. This is what is called staircase modulation or nearest level modulation, which we saw in the first slide, right? We want to approximate a sine wave, and the easiest way to do that is to just apply the nearest value that we can in the staircase shape. And to do that, essentially we have to turn on or turn off these modules at the right time. So what you see is basically when you want high voltage, you can have all the modules on, and as the voltage starts decreasing, you slowly start turning modules off, right? And this is the upper arm voltage. This is the lower arm voltage here, and you can see that they are in 180-degree phase opposition, and that results in an AC voltage that looks like this. Now, of course, there's some sort of hand waving here because this doesn't take into account any filtering filtering effect of these inductors, just doing some, but you get the idea. So you want to generate a sinusoidal shape. The lower arm voltage is in phase, upper arm voltage is out of phase. Both have only positive values, upper arm and lower arm, and that's basically how you do it. Okay, so let me just get rid of all the. I'm sorry. Are you still able to see my screen?
Yes, Abhijit, yes. No issues.
I think my.
Yeah, some other. Yeah.
So this is a very simple case that I've shown you. This is essentially staircase modulation. It's not even pulse width modulation, right? And to look at all the possible techniques, of course, is not feasible in this 1 hour talk. But just to cover, all the possible modulation techniques, there are essentially 4 different types. So we are going to look at staircase and nearest level modulation. Other than that, there's carrier-based, which is the most common PWM that is used in most other converters. There are some people who have done space vector modulation, and there's of course selective harmonic elimination. But with large number of modules and all, generally a lot of practical systems use either some form of carrier-based scheme or staircase or nearest level scheme, because the whole point is there are so many modules. It's just not very feasible to do any more complicated modulation, right? So we've already seen what staircase and nearest level modulation look like. We'll look at quickly at what carrier-based PWM looks like. So I think some of you may be familiar with carrier-based PWM methods. Essentially, what any PWM method does is you have a reference waveform or a modulating signal, which is the black waveform that I've just overwritten in red, and that's your fundamental voltage, right? That's the voltage you want to generate. Now you compare this with a number of signals that are called carriers. Now those carriers are high frequency signals of some predefined shape, and the comparison between these two is used to determine whether certain switches are on or off. In our cases, whether a module is inserted or bypassed, or module is on or off, right? So for the remainder of this talk, I'm going to focus a little more on phase shifted carriers, because that's easier to understand, easier as a tool to understand MMCs. Some people use level shifted carriers also. But also one small point to note is that unlike many other topologies, these modulation schemes don't directly drive the switches, right? So essentially what this will do is it will tell us when switches need to be turned on or off, or when modules need to be inserted or removed. But some additional logic is needed before we can determine which module, because there are so many modules, right? And so we'll come to that next. Okay, if you're doing phase shifted PWM, that results in very nice phase shifted, very nice PWM waveform automatically, as long as the phase shift between these carriers, the carriers assigned to all of these modules, is equal. So if you have, let's say, 4 modules in one arm, trivial case, supposing, just as an example, if you have 4 modules, and you would want 90 degrees phase shift between the carriers that are given to all of these 4 modules. Now, just as an example, what you can see here, let's say this is the first carrier, this is the second carrier, this is the third carrier, fourth carrier, fifth carrier, and so on, right? So what you can see here is, I think this was from a simulation we did for 8 cells, and those 8 are for 4 cells in the top and 4 cells in the bottom, right? And what one can do is that we can have non-interleaved PWM, which means 4 carriers can be assigned to the top 4 modules, and the same 4 can be assigned to the bottom 4. That's one way to do it. Simple. Number of carriers equals half the number of modules, and we are done. But there is a method called interleaved PWM, where we can shift the carriers of the bottom module by half that gap. So essentially what we do is, let me just see if I can draw that here. So erasing call slide. So this is SM1. Let's say that we assign this particular carrier to SM1. What I'm going to do is the next carrier I'm going to assign to this one. The third carrier I'm going to assign to this one. So carrier 1, carrier 2 goes here, carrier 3 goes here, carrier 4 goes here, carrier 5 goes here, and so on, right? So the benefit is that we get smaller steps in the output voltage. So when there is no interleaving, what ends up happening, and I leave this as a sort of thought experiment to anyone who wants to look more deeply into this, is that when there's no interleaving, there'll be one switching on the top arm and one switching on the bottom arm simultaneously, always. As a result, the voltage at this node A will always experience a step, again, sort of hand waving here that, you know, arm inductors don't have an effect, but the voltage at A will have a step equal to one module voltage, right? However, when there's interleaving, we can see that the step now becomes half of the cell voltage. So obviously, interleaving would be preferred. Lower dV by dt, we'd get slightly better voltage profile, slightly better currents, lower harmonics, and so on. Okay, so now getting back to which module to turn on, right? So our modulation scheme tells us, you know, turn on a module or turn off a module, or increase voltage, decrease voltage. Essentially, let's say we are at this point, the modulation scheme says that we need to switch on one module. At this point, for instance, let's say at this point, we want to switch off one module. But which module should be turned off? That is determined by our capacitor voltage balancing criteria. So just to recall, IDC control, the DC current control that we did, was able to control the average capacitor voltage. So we've got the average under control, but changes in individual capacitors from that average also need to be controlled. So the easiest is what is called a sorting scheme. So you first figure out how many modules need to be turned on at any given instant. So for instance, at this point, one module needs to be inserted, right? So when one module needs to be inserted, we figure out which is, first of all, we figured out whether the current is in a charging direction or in discharging direction, because we cannot control that, right? Based on the current direction, we choose whether the lowest voltage submodule is inserted or the highest submodule is inserted, highest voltage submodule is inserted. Essentially, we want to minimize the error between the capacitor voltages from their nominal values. So easiest, of course, is to sort all the voltages. So if there are n voltages, we just sort them on. And when we want to insert, we insert the lowest. When we want to remove, we remove the highest. That's one way of doing it. But there are a lot of other methods that people have done, which are, let's say, predictive control. Because once you know the voltages of the modules, you know the current values, you can sort of estimate which capacitor needs to turn on or which cell needs to turn on when, right? So some predictive methods have already been shown. They're computationally a little more complex, obviously, but they have certain other benefits. There's, of course, some state estimation based, because each capacitor voltage is a state, so you can do some state estimation. And there's some neural network based schemes, and there are some other modified sorting schemes also. So you need not sort them simply by instantaneous voltages. You can sort them by instantaneous voltage plus some cost term, right? So you can do some optimization in that. And in many cases, this capacitor voltage balancing scheme is chosen in conjunction with sizing of passives. So as I've already mentioned, the change in capacitor voltage or the ripple in the capacitor voltage is dependent on IA, which is the current that is drawn from the arm, and also the value of the capacitor, the capacitance, right? It is also dependent to some extent on the arm inductor and what PWM scheme we are using, right? So based on all of these constraints, sometimes it is easy to use, let's say, a rudimentary capacitor voltage balancing scheme, but choose our passives carefully. And commercial systems where the application is very well known and the company is designing it for a very specific use case, this is in fact it's very specific domain knowledge, and they will not reveal it. Okay. So next thing we want to look at is circulating current. So we've looked at models for DC control. We've looked at models for output voltage. Now let's look at circulating currents. So circulating currents are by definition currents that circulate within the controller and don't go out. So we've already seen one example where DC current is flowing from the DC source through the arms and back. We saw that only for one phase. But there is another possible path, and that is among phase legs. So there could be a current that flows from one arm through the other arm and back. And that's essentially because there's a voltage source here, 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 right? So essentially they can set up a voltage in this loop, which can cause this current to flow. So I already mentioned that DC circulating current, which is this path that is shown is essential. We cannot manage without it, because if it goes to zero, then all the capacitors will discharge and topology stops working. But all these other harmonics and all these circulating currents between arms, they must be suppressed. So second is, what are the harmonic components? We need to figure that out. So where does it come from and how to suppress it is what we are going to see. So first of all, when we designed all our modulation scheme, when we designed all our VU, when we designed what VU should be, we assumed that the capacitor voltage is nearly stiff. We assumed stiff DC bus for each module, right? That's obviously not the case. IA, well, or rather, the split of IA by 2 here, that flows through the submodule capacitors. But does it flow continuously through the submodule capacitors? No. It flows only when the module is inserted and stops when the module is bypassed. So the current seen by the capacitor is essentially PWM function multiplied by the arm current, or arm current by 2. Phase current by 2. And the result is that the submodule output voltage will start containing second harmonic. We'll see that. So let's see what this modulation signal was. So modulation signal was this. We know that we want our modulation signal to have, and when I say modulation signal, take it with a pinch of salt. This is sort of the reference output voltage for each module, right? We want each module to generate this upper one fraction of the upper arm voltage. And again, this is in per unit term, so we want it to be like this. IA by 2, we already know, consists of the sinusoidal component which goes out, plus some DC component which I've shown here. Now, this contains DC plus fundamental. This contains DC plus fundamental. So the output is going to have 4 terms and is going to have 3 frequency components. That's fairly obvious from just Fourier analysis. Sorry, just 1 second. Okay, so we were saying that this signal now has 2 components. Somebody, I think, has a question. No? Okay. Okay, so essentially there are 3 frequency components. You're going to get, sorry? Is someone trying to ask a question?
No, sir, you can proceed.
Okay.
So we can take questions at the end. Okay.
No, okay. If anyone has any comments, just feel free to put it in the chat box. If it's addressable right there, I'll do it. Otherwise, we'll take it at the end. Okay, so what was I saying? Yeah, so this has DC plus fundamental. These two have DC plus fundamental. Obviously, the output has the output voltage that is going to be produced here. Sorry, not output voltage right now. We are talking about the capacitor voltage, right? So the capacitor voltage or the current seen by this capacitor is going to have 3 frequency components, and that is going to be DC, fundamental, and second harmonic. Right now, by definition, we have designed our IDC component so that this DC turns out to be 0. So the DC of this times all this, everything should cancel out, and we should not get any DC component. So we know that this is definitely 0. Fundamental we know is definitely not, definitely non-zero. But also we see that a second harmonic component has now appeared. So essentially what I'm trying to say here is that the current that is going into this capacitor or coming out of this capacitor, submodule capacitor current, has this second harmonic ripple on top of it. Okay, so if current in the capacitor has this second harmonic, capacitor voltage also is going to have that second harmonic. And when you multiply this fundamental and second harmonic with the PWM duty cycle, the output we assumed was going to be only fundamental, right? But now we are going to start seeing output also contains second harmonic. Okay, let's see. Can you elaborate why only the second harmonic ripple? Okay, so essentially what will happen is that capacitor current, the submodule capacitor current, is IA times whatever is the average value of the duty cycle, right? Because when the module is off, current does not flow through the capacitor. When the module is on, current flows through the capacitor. So whatever is the current here, the arm current, right, times duty cycle gives us V cell, right? Duty cycle we know is of this form, DC plus fundamental component, right? IA by 2 plus whatever is that DC component, sorry, IA by 2 plus the DC component is what is flowing through the arm. So essentially what we get is we get these 3 terms, right? We get DC plus fundamental plus second harmonic, just from the math. We are not doing anything more. But from our previous discussion, we have already determined that this DC component must be 0. Because if this DC component was there, it would change the average voltage of the capacitor, right? So we don't want that to happen. So this is by definition equal to 0, right? Fundamental will be there because obviously IA by 2 has to flow through all of these, and so that, and second harmonic will be there, right? Now, what this means is, what I'm trying to get at is that this V cell, instead of being DC, is going to have DC plus a fundamental ripple on top of it, plus a second harmonic ripple on top of it. Okay, so now what happens is we expected that the output should be only fundamental, right? Because we want this modulation scheme or this modulation signal to generate a voltage that is again only this, right? DC offset, but only fundamental. So what ends up happening is that when the capacitor voltage was DC, everything was fine, no problem. Or if your capacitors are very, very large, no problem. The ripple doesn't appear anywhere. But when your capacitors are finite, then that ripple will now be multiplied with your duty cycle and appear here. So now what happens is that your output voltage now consists of a second harmonic voltage in the output. Third harmonic, obviously those will also be there. And that second harmonic that appears here, obviously, okay, we should talk about that. So that second harmonic is like an additional voltage that appears here. And that is going to start driving its own second harmonic current. Now, we saw how fundamental current results in second harmonic voltage output. Second harmonic current results in third harmonic current, and so on. So it's a cascade. But every next iteration, the magnitudes keep decreasing. So fundamental is of course the dominant, second harmonic has low magnitude, third has lower magnitude, fourth has lower magnitude, and so on. Other thing is higher harmonics are going to be progressively better filtered out by these arm inductors as well. So we don't need to worry about the higher one, but if we can eliminate the second harmonic, then we are good. Now I'm just going to make a statement here that sort of uses what we have seen for the DC component. What I said was that if an additional voltage is added in upper arm, or the upper arm produces a slight offset voltage, that and a lower DC offset voltage in the lower arm basically have no effect on the output. The case of the second harmonic is exactly this. So the second harmonic voltage is a positive delta on the upper arm and it's a negative delta on the lower arm. I won't go into the details of why that happens. It's very simple. If you draw the circuit, you'll see it. But essentially, it's common mode, so that current doesn't go out. It wants to circulate either through the DC link, or if there are currents in the other arms, then that current, part of that current will circulate through the other arms also. Right? So that's where the harmonic comes from, and that's how the current is generated. And as I mentioned, the system that is seen by the second harmonic ripple source, we can think of it, we can model it as an extra voltage source in series with this arm. And the system seen by it is exactly the same as that for our DC. So basically it sees these two arm inductors, and then we assume that our DC sources have zero impedance at the second harmonic, and so basically this is like a short circuit. So you have only L arm, and of course it's equivalent R arm to stop this current. And this is fairly significant because that arm inductor, that is that second harmonic component, can become significant in certain cases. So how do we solve it? How do we eliminate this? Now, one simple way to do it is, I already said that the second harmonic appears as a extra voltage source in our arm. Can I not just change my VU, which is the arm voltage, to be whatever it's supposed to be, minus whatever is this delta that got added here? So if I can do that, I basically compensated my second harmonic component right here in the arm. And that is what we are going to do. So the question is, what should that compensation be? One more other thing to note is that we want to do it in closed loop sense. We cannot do it in open loop because as you know, the value of that current depends on the exact values of this capacitance, right? Because the ripple depends on capacitor value. We don't know exact values, capacitors age with time, there's so many issues. So we want to do it in closed loop. We want to do measurement, and then we want to cancel that out. So how do we find out? First of all, you take arm current here, you find their average value. That will give you whatever is the DC component that's flowing here, because the differential component is just flowing out on the phase, right? Now, that average component, we have already figured out that the DC component was being controlled to do arm energy balance. So that is already being done. To control the second harmonic, we can do it in DQ reference frame, because we want perfect elimination of this second harmonic component, which means we want infinite gain for our controller at second harmonic. And short of making a PR controller, the easiest way to do it is to run a DQ controller running at 2F, right? So in a normal case, we want a DQ controller that runs at the fundamental frequency. Let's say we wanted to do vector control for the output, AC output of this converter, but because we want to do second harmonic, essentially we just have to have a reference frame that rotates at 2F. Okay? Now the next question then is, what is the reference frame for that 2F? Where should that controller's reference frame be aligned? And the short answer to that is it doesn't matter. Because what we want to do is, we want to create a new voltage here to counter an unknown voltage that is already here. This is our 2F unknown, question mark, and this is 2F star. This is my intervention. It has to only counter this. So essentially what I have to do is that this should equal negative of this and we are good. So it doesn't matter where my reference frame is, as long as it is consistently rotating at double the fundamental frequency. So what I'm going to do is that I'm going to take the PLL that is essentially giving me my fundamental reference, theta reference, just multiply the angle by 2 and I have a DQ reference frame running at 2F. That's all. I don't need to do anything more than that. Okay, so I touched on some of these earlier. The magnitude of the circulating current depends on number of levels, passives, exact modulation scheme being used, and so on and so forth. Also how the capacitors are being balanced, but we won't go into that at the moment. In some cases, I have seen this in one of the system designs that we did. If you don't control it, if you don't have a specific way to control steady state circulating current, that steady state value of circulating current is bigger than the output current. So that is a big problem. So you need to decide whether you need to have some intervention or not. Also, as I mentioned, it's possible to have a filter at 2F, right? It's always possible to have just the inductor designed such that the passive filter will take care of it. And in some cases, let's say based on your design, based on some a priori knowledge of what your load looks like, those things can already sort of determine choices of whether passive filter is enough, or you can just redesign it, or you need some active scheme. Okay, so now let me just get into quickly what some simulation results from a simulation that I already have. And this is a model that is made in Simulink. I'll share a web link where you can, it's a web page where you can browse the model and so on. So let me just see if I can do that. Intranet. 1 second. There we go. Okay, so unfortunately, we are having some network issues with our main departmental server. So I can't show you that at the moment, but let me continue with these screenshots that I took yesterday. Essentially, this is the simulation model that we use. This is one leg, and there's of course 3 of them copies. What this is doing inside this blue box is basically the cascade of 8 modules, 8 cells, 4 in the top arm, 4 in the bottom arm. So this is one leg, and this is the A phase. So what we have here is, first of all, this block is just comparisons. There's nothing more that's happening. VREF is added to all these offsets. That gives us our modulation signal. That is compared to top module ramps for the top modules and ramps for the bottom modules, which I'll show you in 1 second. There you go. So this is where the modulating signal comes in. Right now, it's just fixed frequency, fixed amplitude for this this test that we are doing. But we've used this to do DQ control and PQ injection on the grid side in one of our papers. Okay, so what do the carriers look like ramps for the top module basically are just these phase shifted triangular waves. That's all. There's nothing more than happening. The ramps for the bottom one are exactly the same, except they're shifted. So as I mentioned in the previous slide, the first one goes to the top module, second one goes to the top module of the lower arm, third one goes to the second in the top, and so on. So I've already explained that part. Next one is this block here, which is our IDC control, right? So as I mentioned, we need to add some offset voltage, some delta voltage to the Vref in both top and bottom. So that's what is happening here. Essentially what this does is it measures the average voltage that we want. The desired voltage is just the nominal voltage that has been set times 8. So there are 8 capacitors. You can see VC0 by VC7. These are the 8 measurements that come out. And I'm just going to sum them all. And after I sum them, I want to compare it with this reference value, PI controller, that gives me the offset. That's all. So that's my DC offset here. The next is this 2F control, which is that DQ controller that I mentioned. Essentially is just measuring the 3 2F components, determining what should be the offset on 3 phases, and again supplying that to this one. So if you remember, I mentioned that it needs to be added such that top module gets a positive delta and bottom module gets negative delta. If you get the sign wrong, if you end up adding offset in the same phase, let's say on both of them, then you'll see that instead of affecting this circulating currents, you'll start affecting your output current. So that's a quick check in your module, in your simulation. So if you start seeing effects on the output current, that means your polarities are wrong. Okay, we have a question. Okay, next block is, okay, so just, to tell you what is going on inside this, is basically 8 of these modules, all are half bridges, all in series. Okay, I think there's a question. Share reference for capacitor voltage control and I2F control. Okay, so what I'm going to do is this module is actually available on my GitHub page, but it's not yet public. It's already shared with a lot of people. So what I'll do is I'll document it up and I'll share this model so you can use it as it is. And some good papers for 2F control I've shared. In the end of this presentation, there's a references slide where I've mentioned 2 good presentations that talk about all of these things. There's also a couple of papers which I'll send once at the end of this presentation, I'll add the updated references and I'll send those across as well. Okay, so yeah, so a couple of things of note here are, so these are the modulation signals coming in, 4 modules in the top arm, 4 modules in the top arm, 4 modules here in the bottom arm. One thing that you notice here is that I've had to add explicit L and R, otherwise Simulink doesn't like it. And the other thing that you want to do is, because these are 2 inductors, right, that are driving this node here, I find that it helps simulation much of the time just to add a small solver assistance capacitor here. So I just make this node a voltage node by adding a small capacitor. This is in picofarads, but just it being there helps the solver get things right. Right, so is there anything else I want to talk about in this module? Yeah, so what I'm doing is, just because this is testing, I'm measuring the output voltage of each module. There's an internal voltage sensor that gives me the capacitor voltage of every single capacitor in this topology, and we'll see those capacitor voltages in the results. Okay, so coming to the exciting parts, right? So this is our circulating current control. Basically, I've not shown voltage outputs because those are fairly standard. There's nothing really new there. But the circulating current control is something exciting, so that's why I've shown that. So what these show is, this is without any circulating current control, and this is with. So this one is with the circulating second harmonic circulating control enabled, right? And these three currents are basically, let me just show you, are these three currents here. So IA upper arm, IB in the upper arm, and C for the upper arm. So that would be those are the three currents that you see here. So you can see that there's a significant amount of second harmonic that is flowing in all three. Okay, so you can see that just after I enable my circulating current control, you can see that the second harmonic is eliminated. So in this particular system, of course, you know, the size of the passives and all those things were designed such that this inherent second harmonic is not that high. It is still there, but you can see that in magnitude terms, it doesn't really affect the total current by that much. Of course, it leads to higher loss, so many other issues where it doesn't affect. What you see on the bottom, this trace, is the average value of all three. So that is the DC component that needs to flow through all three modules, right? I'm sorry, from all three arms. And what is important to see here is that that is unchanged. If that were changed, then we would have a problem because our arm energy would go unbalanced, right? So we want to make sure that that does not change. Only the second harmonic has been eliminated. So that's what this slide shows. This one just shows the internal controller output. So I have a DQ. Basically, it's a PLL that does DQ transformation, and it's locked in at 2F, and I'm filtering it also. So this is the filtered value of the D and Q components at 2F, and this is when my controller was enabled. You can see that before the controller was on, both of these are at some significant value, and then my controller is able to bring them down to nearly zero. And what you see here are the DQ values of that offset voltage. So essentially, this is the D value, this is the Q value, Q and common mode is not there. So DQ values are there, and these are converted to ABC standard transformation. But you should remember that DQ to ABC again should be done at 2F, not at 1F. So once that ABC is done, then we add it to the three arms. Okay, we have one more question. Let me just see. Okay, that's just the feedback form that everyone should fill up. And yeah, coming back to the slide. So this is just the controller demonstration. So how does that affect our capacitor voltage ripple? So the idea is not by much, at least it's not visible, but you can see that this is no 2F control. There's a significant amount of second harmonic ripple. And once I have my 2F controller on, you can see that that 2F has disappeared. There's no second harmonic ripple in the capacitor voltage. So that's all I have to talk about today. I think I've covered a huge amount of things. Okay, there are a couple of questions. What switching frequency does it operate? So in this case, I think it's a 1 kilohertz switching frequency that I've used, and 1 kilohertz for the modules, of course. Let me just go over one thing that I sort of skimmed over, and that is right. So the frequency of these carriers, at least in my model, I took it as 1 kilohertz. So the result is that if you have 8 modules totally, you get the effective switching frequency is almost 8 times, right? So each module is not switching at 8 kilohertz, but the output has that effect. Now, then the next question was solar-based MMC. Yeah, so solar-based MMC. Let me just make a few comments. I'm not really expert in that area because I've not really worked a lot in EV-based MMCs. But let me just address this question in a few ways. Number one is that if your PV is somehow linked or connected across these two terminals, right? So basically DC comes in, AC power goes out. That's absolutely possible. The problem is that the application of MMCs is attractive when these voltages here are fairly high. So when these voltages are fairly high, this voltage, this VDC link is actually fairly high, right? So in that sense, I'm not sure if it makes sense to have PV outputs, which are right now, 1.5 kV. I think the latest standards only permit up to 1.5 kV DC link voltages for PV strings, right? So you would need some sort of a solid state transformer or some sort of a DC-DC converter to bring it up again to this high voltage. And I'm not sure if in the case of PV, where maybe utility scale, you have loads of land, there's not really so much constraint in terms of let's say size and weight. So it may not be the best way to connect PVs using this arrangement. There are some studies, there are some research papers where PV is interconnected to this submodule, right? Or these submodules. That's not really a classic MMC. That's more of it's more like a cascaded H-bridge type converter. But the problem is you can't manage power differences between modules. So that is a big challenge, because you see what happens is the same current is flowing through these through all the modules, and you want them to be generating roughly the same voltage, right? So if that power varies, then we have an issue. So if you have partial shading in PVs and all that, then it's a little challenging. There are people who have addressed it, and I would recommend you to look at some of the research papers to get some idea about that type of converter. But it's not exactly MMC in the strictest sense. Okay, so next question is arm inductance. How is arm inductance calculated? So roughly speaking, arm inductance is calculated to act as a filter. So the first reference that I have provided that has some discussion of this arm inductor design, and there's basically a lot of involved process in figuring out what your C and L should be, the passives design, and it's more to do with system level considerations than purely electrical considerations. So I'm not going to go into too much detail there, but essentially arm inductors are filters that basically do filtering of the submodule output voltages or arm output voltages. So they work in the switching frequency domain, but they also do this DC current control. So you don't want arm inductors to be too small, because then your DC current control becomes difficult. But you don't want it to be too large, because then first of all your dynamic response becomes poor, plus size of inductors at fundamental frequency is always a bone of contention. Next question was how capacitors are sized. So theoretically capacitors are sized by just looking at ripple. So you design your topology, figure out how much is your acceptable ripple based on your output load current, IA, IB, IC. That tells you how much current is flowing through the module. That tells you capacitor value. However, there are other considerations like life. There are considerations of temperature, loss, and all those things. So I have a feeling that industrial designs would consider all of these things, and not just the electrical requirement, which is some, let's say, 5% ripple in the capacitor voltage. Okay. The next question is, if we say that MMCs have less harmonics than two-level converter, why can't we use it to drive a motor and reduce heat dissipation and other losses? Okay. So first thing is, MMCs are not okay. So let me address this first. MMCs have significantly higher complexity. They are way more complicated to control and modulate than two-level inverters, right? So if you have devices that say can operate at 1200 volts or 600 volts or whatever your system requires, then just use those. There's no reason to add more complexity, because if you have N modules, you need N isolated power supplies to drive the gates. You need sensing. You need gate drivers, there's so much more complexity, right? So nobody is going to select this just for reducing harmonics. Second thing is, we've talked about MMCs in grid connected applications where the fundamental frequency or the output fundamental is nearly fixed. There's no case where your output voltage needs to be at lower frequency, whereas in motor drives you may have to operate at very low frequency, right? So there are now applications of MMCs where researchers have looked at using MMCs for motor drives, but it is significantly more challenging because as that as frequency goes down, for the same ripple value you need larger and larger capacitors. So these capacitors will become larger and larger. So that's one challenge. People are looking at it. So I advise you to look at some papers on MMCs for motor drives. They are attractive for industrial level, industrial voltage level, medium voltage motor drives. Okay. Next question is how do you decide phase shifts or phase angles for I'm assuming PSC PWM is phase shifted carrier PWM. So there what we do is, if we have n total number of modules, right? Or let me be clear here, n modules in the top, n modules in the bottom. So we have 2n total number of modules. We are going to have 2n number of carriers, right? And those 2n carriers are going to be spaced equally apart, right? So 2 pi is going to be divided by 2n for 2n total modules. Now, when you want interleaved PWM operation or interleaved carriers, all we do is we assign the first carrier to this top module, next carrier to the top module here, third carrier here, fourth carrier here, and so on. That's the easiest way to do it. Okay, next is share access to GitHub link. Yes, I will do that. Right now, I don't have access to our institute local intranet because of some power failure. But as soon as that happens, I'll share the link with the organizers. They can send it out to you. Next one, practical application of MMCs in general. HVDC, that was the most popular and most sort of sought after use for MMCs. I covered that in the first few minutes of my talk. Then, since MMC has large number of CE switches, it could have appreciable conduction loss. Yes, absolutely. It has much more loss. However, it is used in applications where it is not possible to have a single device anyway. So let's say your this grid voltage is something like 35 kV, right? If this 35 kV, after accounting for things like headroom and all, this voltage is 60 or more kilovolts. There is no device that will have 60 kilovolt blocking rating. And so somehow or the other, you have to have devices in series, right? So when you have to have devices in series, you have to have, they will obviously have conduction losses. But it's like there's no alternative. You cannot have one 60 kV device anyway. Okay, so next.
Is there any more questions?
Yes, there are a few more questions. I think people have sent me questions in private chat. So I'm just trying to go in order so I don't miss something. Okay, fault tolerant condition. How does MMC behave with respect to DC short circuit? That is a very good question. What happens is that there are a lot of studies on fault, DC side fault response of MMCs. Yeah. Yes, somebody is asking something. Okay. So there are a lot of studies. I'm not going to go into the details, first of all, because I'm not an expert in that. And second is that is sort of beyond the scope of this discussion right now. But to give you a flavor for what it is, essentially when there's a fault, right, it causes a short circuit. So you need to be able to control that DC current. Now, to control DC current, there's only one way to do it. You have to apply, or you have to inject a DC voltage in that path. And to inject DC voltage in that path, you have only your upper arm and lower arm that you can control, right? So in order to suppress that fault current, you need to be able to oppose that fault current, right? Your voltage that is applied should be able to oppose it. And to do that, you need modules that are other than half bridge. Half bridge cannot generate negative voltage, so you cannot do anything. So things like full bridge modules, or there are some kind of cross-connected modules. There are a lot of other topologies for modules which can do that. So those are required to do faults. Then,
Dr. Abhijit, Dr. So can we request the rest of the questions to be mailed to you by the participants, because we have some time constraints right now.
Yeah. Sure. I'll just quickly go through some questions. If anything is arm inductance, I've already talked about. Voltage ripple, I've already talked about. Advantages of MMC over CHP. Very simple. There is no single DC link in MMC. You remember when you want to do AC to AC, there is no DC link at all, right? Advantage of MMC over CHB in STATCOM applications, I would argue that there is no difference between MMC and CHB. So what is the meaning of a CHB in STATCOM? Doesn't it become an MMC? So I would encourage you to think about that. Then last one is, yeah, I think I've addressed everything in.
Yes, I think Abhijit, you can show the last slide. I think that reference that you are talking about.
Yes. So these are two good sort of presentation slides that talk about all of the considerations, system level considerations for MMCs. I will add a couple of good papers that I have used and I have referred to. So I'll add that when I send you the updated slides. Okay.
Okay.
And so just a few acknowledgements. I wanted to specifically acknowledge Person Edmohan for letting me do all this. And two students in that group, Anushri and Jairam, they helped me a lot with modeling, making the models. A lot of the diagrams were made by them. And some of this work is sort of the foundation for one of the papers that we published in Compel in 2019. So thanks to them, and thanks to the organizers for today's event. Over to you, sir.
Thank you, Dr. Abhijit, for the very informative presentation on modular multi-level converters. You started with the fundamentals of MMCs, then you discussed about the various circuit topologies for MMCs, then the modulation techniques. Then you detailed and explained the various modulation techniques used for multi-level inverters. Then you touched upon the capacitor voltage balancing scheme for MMCs. Then the circulating current control, what are the techniques being used for circulating current control. Then you touched upon that simulation part also.
Thank you.
With regard to MMCs. And we had a very good interaction from the participants, and we had today over 140 plus participants from across the globe.
Great.
It's a very nice participation actually, and they interacted us very well also. And that shows the interest in this topic, and basically the resource person also, they are interested.
Thank you.
And thank you all participants for attending the seminar. And I also thank Dr. Vasanthi, our secretary of our chapter, and Dr. Bijana, chair of IAS Kerala chapter, and the panelists today, Ruben, Eldo, Alan, etc. Thank you all. Thank you all for the support. And again, once again, I thank Dr. Abhijit Kshirsagar for your valuable time. We all know that even though it's a lockdown period, we have online classes and all, research works and all. In spite of your busy schedule, you agreed to deliver this webinar. So thank you all. So thank you.
Okay. My contact information is here on the screen. You have my, you can find me on LinkedIn, on my IIT profile page also. I welcome emails if you have any questions. And Yeah, that's all. Thank you.
And you can also tag your questions on the feedback form. There's a section provided to ask queries. Will you be sharing the feedback form with the presenter? And you can also tag the questions in the mail sent, the reminder mail sent to you, if any, because there are a lot more questions are here, but
Sure.
due to time constraints, we can't
Sure.
discuss all right now.
Absolutely. Sure.
So thank you all. Good night.
Thank you. Good night.